Welcome to Chemistry 418, Nuclear Chemistry. This is Lecture 1, an introduction to the course, and a discussion on nuclear data that's available that we will be using throughout the course. The material that will be covered in this part of Lecture 1 is provided here. We'll start off with an overview and a discussion of the atom and the nucleus. I suspect this is review material for most of you. We'll talk about the history of radiation research, discuss the overlap between the early days of nuclear physics and radiochemistry, and then we'll move into how radioelements were discovered, focusing on those that were anthropogenically synthesized. We'll discuss the chart of the nuclides and available data. We'll describe the use and give some examples of the data, primarily focusing on half-life and decay modes for this lecture and this part of the course. We'll also introduce terms common within radiochemistry, particularly terms such as isotopes, which we've discussed and I'm sure you've heard previously in courses. And we'll also discuss the limit of the course, which really starts to abut high energy nuclear physics. The goal for this lecture is to really have an understanding of decay modes and comprehension of half-life. Other terms, concepts, and ideas outside of decay modes and half-lives will be presented in this lecture and discussed in further detail later in the course. The figure here represents the isotopes as shown in the chart of the nuclides. The black boxes represents those isotopes that are stable. As you can see, there's a trend and a line that starts off with hydrogen and goes all the way up towards bismuth for the stable isotopes. For any given isotope, you can see that there are radioactive ones, which are neutron deficient. As example here, all these blue ones, which represent electron capture or positron decay. The red ones here, they have excess neutrons compared to those stable isotopes. They tend to decay by beta minus emission. The yellow ones, so you can see they tend to be in a higher mass region. And these represent isotopes that decay by alpha emission. And a few of these green ones, as shown here, very heavy isotopes, represent those that decay by spontaneous fission. The figure here should be familiar, as it is a basic representation of an atom with a core that is the nucleus, surrounded by electrons, which represent the bulk of the space. This figure, of course, is exaggerated, where by far the vast majority of an atom is occupied by the electron cloud, and only a small amount, which wouldn't be visible in this picture, is occupied by the nucleus. As we describe an atom, it's composed of electrons that surround the nucleus. The chemistry of this atom is based upon the electron behavior. The electrons, as we know, are negative particles. The nucleus contains the bulk of the mass of the atom, and it is composed of neutral neutrons and positive protons. The properties of a given element are based on the number of protons and corresponding number of electrons. The neutron number generally does not greatly affect the chemistry of a given isotope. Nuclear properties, however, are based upon the number of neutrons and protons that are contained in the nucleus. You could think of whether or not an atom is stable based upon its number of neutrons and protons. As we'll see, there's a ratio of neutrons to protons that will induce a stability into the nucleus, forming those stable isotopes. The caveat being that stable isotopes are primarily from elements below bismuth, those that have proton numbers of 83 or less.
we will see that there are two elements below this number which are in fact only composed of radioactive isotopes.
You can think of this as similar to oxidation states in elements, where the number of electrons that an atom can manage are limited. You can think of iron. Iron can be 0 plus, right? It can be metallic. It can be +2, or it can be +3. To make iron atom that is +1 or +4 can be done, but it's unstable. It's not its natural configuration. Similar to the nuclear properties, where the nucleus has a stable configuration based upon the number of neutrons and protons. Now let's review some of the basic properties of atoms. Likely you have seen this before in previous classes. So elements have different isotopes. Elements are defined by atoms with the same number of protons, and here I'm going to call protons by the letter Z. So in the course, if you see a Z number, it means the number of protons, and different number of neutrons. So isotopes all have the same Z, they're that element, but they'll have different neutron numbers. The chemistry of these isotopes are fundamentally the same. We will see some instances where we can separate isotopes. Often that's done through physical properties. As an example of isotopes, we can look at hydrogen, as shown here, where we have hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 1 is a proton, hydrogen 2 is also called deuterium, and hydrogen 3 is tritium. Of these isotopes, hydrogen 1 and hydrogen 2 are stable, while hydrogen 3 is radioactive. There are over 3,500 known isotopes, and a little over 250 of them are stable. So the bulk majority of isotopes are radioactive. Another thing we can compare is the size of an atom. Protons and neutrons in the nucleus have a radius of about 10 to the minus 14 meters. Electrons around the nucleus, the ionic radius, that's on the order of an angstrom, which is 10 to the minus 10 meters. So most of the space in the atom is occupied by the electron cloud, and most of the mass is in the nucleus. Now, when we talk about the mass of the nucleus, we can compare these masses as shown here for the mass of an electron, a proton, and a neutron. And I do want to point out here that I am providing the masses in energy units, mega electron volts, MeV. We'll see that the electron mass is about a half a mega electron volt, while a proton and a neutron have masses that are approaching 1,000 mega electron volts, MeVs. We'll call mega electron volts MeVs. So by far, the proton and the neutron are much more massive than the electron. So if we look at an atom, and we can look at the pictures here given for hydrogen isotopes, we can see that the bulk of the mass is indeed in the nucleus, while the cloud occupied by the electron has most of the volume. And I do want to point out that MeV is an energy unit, and we are using the relationship between energy and mass, E equals mc squared, to interrelate the two. Now from this, one atomic mass unit, which we use in chemistry, AMU, is equal to 931.5 MeV. And we'll discuss this in a little bit more detail when we talk about masses and their effect on nuclear properties in the next lecture. But the mass of an atom is not equal to the number of protons and neutrons. So for instance, carbon-12 is actually less than the mass of 6 protons and 6 neutrons. If we look at this figure here, we'll see that the mass of the nucleons, the neutrons and protons, exceeds the mass of the nucleus. So the mass of an atom is less than the sum of its total neutrons and protons. Where does that mass go into? We'll talk about something called binding energy. Imagine that extra mass can be converted into energy, and that energy helps keep the nucleus together. The numbers of nucleons in the nucleus, neutrons and protons, and how they relate to each other has an impact on radioactive decay and hence radiochemistry. So the combination of protons and neutrons that are in the nucleus influence the stability of that nucleus. And let's examine this by looking at some elements. Let's look at carbon. Carbon-12, carbon-13 are stable. All carbon isotopes are going to have 6 protons. Carbon-12 has 6 protons, 6 neutrons. Carbon-13 has 6 protons, 7 neutrons. These two isotopes are stable. The ratio is about 1 proton to 1 neutron. All other configurations for 6 protons are unstable. So for instance, carbon-11 is a positron emitter. Carbon-14 is a beta emitter. They're radioactive. Carbon-14 is used in carbon dating, and we'll talk about that when we talk about decay and how isotopes can be used to determine the age of materials. The other thing we should point out is that you should have some familiarity with this nuclear property of carbon if you've done carbon NMR. Carbon-12 does not have a spin because the even number of protons and the even number of neutrons pair up. There are 3 proton pairs that are pairing the spin, and there are 3 neutron pairs that are pairing the spin. So the overall spin of the carbon-12 nucleus is 0. If we add an extra nucleon, in this case the extra neutron, there are 7 neutrons. There's 1 neutron that is left unpaired, and the spin of the entire carbon-13 nucleus is based upon the spin of that unpaired nucleon. And when we discuss the shell model, you'll be able to use this concept to predict both the spin and parity of isotopes that have unpaired nucleons. Moving on to lead. Lead has 82 protons, so every isotope of lead starts off with 82 protons. The stable isotopes are listed here: 204, 206, 207, and 208 lead. So they have 82 protons and then 122, 124, 125, and 126 neutrons. Unlike carbon, which has about 1 proton to 1 neutron for a stable isotope, the lead has about 1 proton to 1.5 neutron. So as the nuclear size increases, the ratio of neutrons to protons increase. Again, at carbon with 6 protons, so a Z is 6, that ratio for a stable isotope is 1, whereas lead with a Z of 82 protons, the neutron to proton stable ratio is about 1.5. So any isotope that isn't within the stable regime will release energy to form a more stable nuclear configuration. And that's radioactive decay. During that decay, the nuclear mass gets converted into energy using E = mc squared, and the resultant progeny is at a more stable state than the parent. Based upon what we've just discussed related to the neutron and proton number and the stability of an element, we can explore the periodic table and identify those elements that are only available as radioactive isotopes. We'll call those the radio elements. Here's the latest periodic table. I'm going to call your attention to the heavier elements. That you should notice that there are 118 named elements on the periodic table. Some of the more recent ones include flerovium, livermorium, tennessine, oganesson. The UNLV radiochemistry program was involved in the discovery of tennessine. As a graduate student, I was fortunate enough to work with Glenn Seaborg, who has an element named after him, when academician Flerov, who has element 114 named after him, with the Flerov Institute, visited UC Berkeley. His English wasn't very good. I speak some Russian, so I took him to San Francisco. We went to Chinatown, and I got to hang out with him. That was a very interesting time. Technetium, which is shown here, sits right in the middle of the periodic table.
is a radioelement, only available as radioactive isotopes. Promethium, another element that one would think should be stable, is not. And then elements above bismuth, so elements with proton numbers greater than 83, are all radioactive. So polonium, astatine, radon, all the actinides shown here, and then the transactinide elements. At the University of Washington, one should note that astatine, this element, is produced. Astatine 211 is made at the cyclotron at the University of Washington, and it's used as a radiopharmaceutical.
An example of a publication that demonstrates the synthesis of a new element is shown here. This is from 2010, and it involves element 117, which today we know as tennessine. The UNLV radiochemistry program, which I am part of, was involved in the discovery of this element. I did want to point out that these experiments are often large international collaborations. For this experiment, the team included researchers from Russia and the United States. The experiment lasted around 6 months, and 7 atoms were observed. The output from this publication resulted in the identification of a new element and the expansion of our knowledge of the periodic table. The figure here, the chart of the nuclides, showing the known stable and unstable isotopes, is an expansion of the figure on the first page. Here we can see the proton number, shown as Z, the neutron number, those stable nuclei, indicated by the black squares, and all the other being radioactive. The positron emitters, shown here in red, are neutron deficient. As you see, their neutron numbers would be less than those of the stable isotopes, where beta minus emitters, shown in the blue, have neutron numbers that are greater than the stable isotopes for a given element. Alpha emitters tend to be in the heavier masses of the nuclides, as shown here, generally above lead of 82. And then finally in green, there are some isotopes which are predominantly spontaneous fission emitters, and those are some of the heaviest elements there are. What is shown here is the summation of all the isotopes and demonstrating that around 250 are stable or very long-lived. There's also this term here, magic numbers, which we will discuss in more detail when we describe nuclear models. And you can think of these as neutron and proton numbers that instill extra stability into the nuclei. In a lot of ways, these are similar to electron configurations which make elements inert. So the noble gases have configurations where those electrons fill the orbitals, and what we'll see is that these numbers shown here represent neutron and proton orbitals that are filled. The chart of the nuclides is one of the main databases for radiochemistry applications and nuclear data. An example of the blown up section of the chart of the nuclides is shown here. Again, Z is shown on this axis. The neutron number N is shown this way. So we're starting off with neutrons. We'll go to hydrogen, helium, lithium, beryllium, boron, etc. We move up. Then we move higher in mass with N. And an example is shown here. This is what you would see, and we're going to emphasize online resources. You can click on an isotope. So in this case, I've shown lithium-8. Gives you some information about that nucleus. Tells you the half-life. The half-life of lithium-8 is 838.79 milliseconds. and it decays by beta minus, 100%. And there's a beta minus alpha, which is also 100%, because that means that it decays here, and then this isotope makes an alpha. So beryllium-8 actually does split into two alphas. Resources that can be used are shown here. We're going to emphasize in our course the nuclear data that's at Brookhaven National Laboratory. The website is shown here. It's NNDC, the National Nuclear Data Center, brookhavennationallab.gov. A similar database is also available from the IAEA. Its link is shown here. And I also have the IAEA isotope browser on my phone. And you can do the same. You can download it from your app store. The primary nuclear data that we will use in the course is from the chart of the nuclides. Again, this figure that shows all the isotopes, stable and otherwise. We've seen this elsewhere in the lecture. The site can be accessed through the NNDC, the National Nuclear Data Center, brookhavennationallab.gov. When you go to this site, you can navigate to the chart of the nuclides, and this allows you to obtain data on any isotope. As you can see, there's a host of data that one can find. Right now, we just want to focus in on half-life and decay modes. So these are both accessible. We can type in the isotope we're interested in, and let's look at protactinium-229 since it's one of the questions. We get the isotope, we get the half-life, 1.55 days, and we get the decay modes. This is E, electron capture, which is 99.5% of the time this occurs, and the other 0.5% is from alpha decay. So there are two decay modes for this isotope. You can get this information from any isotope. You don't necessarily even need to go here. We can hover over the isotope, and as you can see, the information will appear. Now, if we go and look at thorium-229, which is here, I just want to show this. You get the spin and parity, the 5/2 plus. We'll talk about that in more detail later in the course. And you get a half-life here of 7,907 years. I want you to remember that number. And the decay mode of 100%. We will reference back to this site throughout the course, and we'll expand the data that we search for based upon the topics in which we'll be exploring in the various lectures. Another data set that's available is from the IAEA, and one can find this by searching for the IAEA. That's the International Atomic Energy Agency, chart of the nuclides. The URL is listed here. And again, it's very similar. You see the same figure. We could scan over the figure if you wanted to try to figure out which isotope you could pick out from there. Or you could do as we did before, write the isotope. And you see we get the protactinium-229. Here's a host of data. The data is also available down here. And again, here's the spin and parity, the half-life in seconds. The decay modes, EC is electron capture, and A alpha, and you see the percentages. Again, a host of other data is available. We can click on this data when we need to get to it. And as I said, we also wanted to look at thorium-229, which is over here. We can go click on that. Again, spin and parity, decay modes. Now the half-life here is 7,880. That differed from the data from the National Nuclear Database. $7,907. So I just wanted to use this as an example. There aren't many examples, but thorium-229 is an interesting isotope in that the data that's available for it for the half-life can vary depending upon the source. So that does also tell you that sometimes you may need to reference your source, or if problems are assigned in which calculations are performed using the data, I'll often put it uncertainty to account for different data sets.
You can also get data on your phone through the IAEA isotope browser. The URL for the isotope browser is listed here. It provides an overview and description of the app. You can download the app from the App Store on your phone. When you do this, you can access from your phone data, as we've seen, similar to the chart of the nuclides. This can include Q values, energy, half-life, and other data. And what this would look like is shown here. On your phone would be the isotope browser. You can put in an isotope. For example, here is carbon-14. Go is selected. This provides the isotope with the number of protons, the half-life, the spin imparity, and the decay modes. Clicking on this further yields a host of data, which includes the proton number, the neutron number, the spin imparity, the half-life, the parents of this isotope, the decay modes, and Q value, binding energy, and other data, which will be useful later in the course. We will discuss the chart of the nuclides, and I'll use a hard copy of the chart. And this used to be used in the course. However, it hasn't been printed in a number of years, and if one goes online to see how much a chart of the nuclides cost, getting one is on the order of $700–800, so we're not going to assign it. That's why we're going to rely on online sources. But you will still see this in the course, so discussing what the information is in the legend from the chart of the nuclides will have relevance for information that's presented in the course, and also understanding some of the online resources. So the information that's in a certain square that describes the isotope is shown here. One is the decay modes. So we have the different types of radioactive decay. They're listed here. Some of them are pretty straightforward. Alpha for an alpha particle, beta minus, beta plus, etc. I do want you to note that the epsilon, the Greek symbol here, is used for electron capture. And then there are some other decay modes which are a little bit less common, like these two beta over here together. That's double beta decay. And if you see something that looks like a cluster, well, that's cluster decay. The time units are provided here. Normal, except for years, they use A from the Latin anno. So seconds, minutes, hours, days, and years will be the time units that you will see. Other symbols include cross-section, which was given in barn. And you'll see some Greek symbols that will describe a decay mode as being weak, so an absolute abundance less than 1%, or very weak, or very, very weak. So 10 to the minus 3 for weak, and 10 to the minus 6% for very weak. Then there's some color associated with the information, and the neutron absorption properties are shown here. So barns, larger barns are shown in this pale blue. This pale green is 100 barns to 500 barns. The yellow is 500 to 1,000 barns. So now it's getting very high. And the red is very high barns. And for half-lives, there's also color. Days are listed in the orange. Yellow, 10 days to 100 days. The light green, 100 days to 10 years. This pale blue, 10 years to 10 to the 5 times 10 to the 8th years. And then the gray is 5 times 10 to the 8th years or stable. So for the half-lives, if you see something in gray, you know that it's long-lived. And similar relationships between the color and the fission yields. So for instance, you can look at this, they're shown here. So from this, you should be able to quickly assess differences in data. So if you're asked for a series of isotopes and what's the longest half-life, what you could do is look at the colors, and if any of them are gray, that tends to be the longest, but then it'll be this pale blue or this pale green. The legend of the chart of the nuclides is useful for demonstrating the information that's provided in the database. The chemical elements given, so for instance, as shown here for lithium, the atomic mass on the carbon-12 scale. There was a time when oxygen-16 was used as the scale, the name of the element, and then the thermal neutron absorption cross-section in barns for the element, followed by the integral cross-section, also in barns. For a stable isotope, which is listed in gray, stable or very long-lived isotopes are in gray. You get the symbol, the mass, the atomic percent abundance, the ground states of even Z, even the ground state spin and parity, as we stated earlier. Even nuclei are 0 plus. The thermal cross-section in Barnes leading to isomeric and ground state, and the resonance cross-section in Barnes, isomeric and ground state. This triangle here means that this isotope is produced from the fission, and this is the mass of the isotope. We will describe cross-section in more detail when we discuss nucleus. Moving on to the radioactive isotopes. Their mass and symbol shown here. It's non-gray. The color has to do with the half-life of the isotope, which can be seen in the legend. Spin and parity, again, 5/ minus is 5/2 minus. The half-life, 10.98 days. The modes of decay followed by their energy with MeV for alpha and beta, KeV for gammas. So this decays with an energy of 0.805 MeV beta. So beta is listed here. The gamma is 91.1 KeV. The cross-section information and the beta disintegration energy. As you see, the beta disintegration energy is a little bit higher than the beta decay energy, so some of the energy is going elsewhere, possibly to a gamma decay. And then again, this triangle says that it is a fission product from the slow neutron fission of uranium-235. Okay, here are some naturally occurring radioactive isotopes. The gray, again, it's stable, but these are long-lived, so it's long-lived or stable. This black bar, this is the indicator that it's naturally occurring. So lanthanum-138, a spin of 5 plus. This is the abundance, so 0.09% of lanthanum is this isotope. The half-life is 1 × 10 to the 11th years. So 1 × 10 to the 11th years, if Earth is 4.5 billion years old, the half-life is longer than the age of the planet. Again, modes of decay, E, this E here is electron capture, beta minus, gamma, cross-section information, and isotopic mass. And this square, as opposed to the triangle, means that it's a shielded fission product. It's still a fission product, but we'll discuss what shielded means. It means that there's a stable isotope in front of it, so it doesn't get fed along the 138 decay chain. Other information is shown here. This is a historic symbol. So lead-210 was also known as radium-D. It was the fourth daughter down from the decay of radium. So historically, you've got this name radium-D. That'll be shown. You'll see some boxes that are split. So this is a metastable state, ground state, so metastable state, spin and parity, half-life, decay modes, ground state, spin and parity. This is stable, so this is the atomic abundance. And then 2 isomeric states that are both radioactive, so tellurium-131. The metastable state, spin and parity, 11/2 minus. Ground state, 3/2 plus. The half-life of each state, and then the other data as we discussed. Moving on to the radioactive isotopes. Their mass and symbol shown here. It's non-gray. The color has to do with the half-life of the isotope, which can be seen in the legend. Spin and parity, again, 5/ minus is 5/2 minus. The half-life, 10.98 days. The modes of decay followed by their energy with MeV for alpha and beta, KeV for gammas. So this decays with an energy of 0.805 MeV beta. So beta is listed here. The gamma is 91.1 keV. The cross-section information, and the beta disintegration energy. As you see, the beta disintegration energy is a little bit higher than the beta decay energy, so some of the energy is going elsewhere, possibly to a gamma decay. And then again, this triangle says that it is a fission product from the slow neutron fission of uranium-235. Okay, here are some naturally occurring radioactive isotopes. The gray, again, it's stable, but these are long-lived, so it's long-lived or stable. This black bar, this is the indicator that it's naturally occurring. So lanthanum-138, a spin of 5+. This is the abundance, so 0.09% of lanthanum is this isotope. The half-life is 1 × 10 to the 11th years. So 1 × 10 to the 11th years, if Earth is 4.5 billion years old, the half-life is longer than the age of the planet. Again, modes of decay, E, this E here is electron capture, beta minus, gamma, cross-section information, and isotopic mass. And this square, as opposed to the triangle, means that it's a shielded fission product. It's still a fission product, but we'll discuss what shielded means. It means that there's a stable isotope in front of it, so it doesn't get fed along the 138 decay chain. We also stated that the fission yields for a given isobar can be identified in the chart of the nuclides. Here's an example. It says fission yields of uranium-233 and plutonium-239. The 239 is in parentheses. So for a given isobar, for instance, this 102, this 2.4 is for the fission yield of uranium-233. Plutonium-239 is in parentheses. So 1.6% of the time, it produces, when plutonium fissions, it produces a fission product with a mass of 102. Uranium-233, when it fissions through thermal neutrons, 2.4% of the time, it produces a fission product with a mass of 102. And I do want you to note that if you look at the plutonium values, they go from 5.4, they peak at around 7, and they start going back down to 2.2%. So something that's close to 7%, 6% is a very high fission yield. There's similar data for fissions from uranium-235. You see it's just on this side. And again, these numbers, they go from 0.03%. They can go even lower. And they shoot up all the way up to about 6.2%, going from an A of 125 to 140.
Let's discuss the decay modes that nuclei can undergo in order to lose energy and transform into a more stable isotope. First, we'll start with alpha decay, based upon the Greek alphabet, alpha, beta, gamma. So this is the first one in order. And the alpha decay is the emission of a helium nucleus from the excited nucleus. For alpha decay, the isotope loses 2 protons and 2 neutrons. That's what's contained in the helium nucleus. So this creates a lighter element of a different isotope. It loses 2 protons, so it's Z-2, and the mass, it loses 4, so it's A-4. Alpha particles, in terms of a particle emitted from a nucleus, are pretty massive, and they can be readily stopped by air, paper. Shielding from them from external sources is pretty straightforward. And here's an example of alpha decay. We have Seaborgium-263 that has 106 protons. It emits this helium nucleus, the alpha particle, and the progeny that's made is Rutherfordium-259, right? 263 minus 4 is 259, and it loses 2 protons, so it goes from element 106 to Rutherfordium, which is element 104. On the periodic table, it would look like this, where Seaborgium, element number 106, 106 protons, loses 2 protons and makes an isotope of element 104, Rutherfordium. I do want to point out here that often for radioactive isotopes, they will have the number in parentheses as an indicator of the most stable or longest lived isotope of that element. The second decay mode we'll discuss is beta decay. This is the radioactive decay process in which A remains the same, but the proton and neutron number changes. So fundamentally, you're converting a proton into a neutron or a neutron into a proton. There are three types of beta decay. First one we'll discuss is beta minus decay. It's written as the beta here. And this is the emission of an electron from the nucleus, converting a neutron into a proton. So in essence, those isotopes that are heavier than the stable isotopes, they're neutron rich, so that neutron can then be converted into a proton. It moves its way up the periodic table. So an example here, iodine-131 with 53 protons. That decays by beta into xenon-131. The A remains the same, but the proton number changes from 53 to 54. There is also the emission of the antineutrino, which is shown here, and this beta minus, that is the electron. And of course, energy is one of the outputs of the decay. A second type of beta decay is electron capture, and this is represented by either EC or the lowercase epsilon. In this case, the nucleus absorbs an inner electron, converting the proton into a neutron. You can kind of think of this as the opposite of beta minus decay, one in which the electron moves out of the nucleus. In this case, an electron moves into the nucleus. An example of this is shown with aluminum-26. It captures one of its atomic electrons. It makes magnesium-26. Aluminum has 13 protons, magnesium has 12. There's a neutrino that's also produced, and energy. And as this is showed in the periodic table here, the aluminum is converted into magnesium, but the A remains the same. Final decay mode is positron decay. Positron is the antimatter electron. So it's antimatter. It's emission of this positron from the nucleus. So for an example, sodium-22 emits the positron with the neutrino. Again, this was the antineutrino. This is antimatter. This is matter with some energy. One of the protons is converted into a neutron, so it goes from sodium-22 to neon-22. As again, in the periodic table, it would show that sodium gets changed into neon. We will learn that positron emission with the isotope fluorine-18 is used in medical imaging to evaluate physiological behavior. Gamma decay is the de-excitation of an excited nucleus. And this de-excitation occurs through the emission of a photon, so light. And what we see here are a few figures. One shows plutonium-240 in an excited state. It emits a photon, it de-excites, and now it's back to being plutonium-240.
In the ground state.
Another way of viewing these excitations is shown here. This is from the table of the isotopes, and it shows the isotope molybdenum-99M decaying by beta emission, and it decays to technetium-99. And this decay occupies some excited state in the technetium-99 nuclear state. As we see this ground state here with a half-life of 2.11 times 10 to the 5th years, is shown here at the lowest energy. We will learn more about the table of the isotopes in later lectures. But what this shows here is that the molybdenum, it can occupy a number of different states in this technetium-99 nucleus. And one of the states that it does occupy is this excited state that's shown here with a half-life of 6 hours. And this excited state de-excites through photon emission
at about 142 keV of energy.
Now, the reason I'm taking some time to talk about technetium, and this is actually technetium-99M, this 6-hour half-life, M means metastable. This photon that's emitted, the 142 42.6 keV photon. That is the workhorse of medical imaging. So technetium-99m is an isotope that's used in about 80% of radiopharmaceutical applications, and it's used to image functions in the body. For instance, there's a molecule, trade name is called cardiolite, that is injected into arteries that feed the heart. As it's decaying and emitting a gamma, one can image the artery that it is in, and they use this to determine if there are blockages in arteries that feed the heart. Now, this decay scheme that's shown here, you should have some familiarity with this from molecular decay schemes. So think about it in the analogies in this way, where we have excitations for molecular states. We have a ground state. We can excite them to different excited states. They will de-excite. Here's an example. There's two routes that we've used to look at this. This includes, let's say, both vibrational, rotational, and UV type excitations. So there are similarities between how we describe molecular excited states and how we describe these nuclear excited states. In an additional note, these photons that are emitted from the nucleus are called gamma rays, while X-rays are photons that are emitted due to electron de-excitations. They're both photons, but X-rays come from the electronic de-excitations, where gamma rays come from the nucleus.
All right, let's start discussing some radiochemistry information.
We'll see how the history of radiochemistry development is linked with that of nuclear physics,
and how they played off each other, and some of the roles radiochemistry played in how we understand physics today. So, a little over 100 years ago, in 1896, Becquerel discovered radioactivity. Becquerel had this salt, this potassium uranyl sulfate, and he exposed it to sunlight, and he wrapped it in photographic plates, and he put that in black paper. So the photographic plate at the time, if you think about it, it's still kind of early material back in the late 1800s. The plate, when they were developed, they showed this image of the uranium crystals. And what Becquerel actually thought is that
the uranium crystals
absorbed light, and that this uranium salt fluoresced and gave off that light. That's what he proposed. And for this proposal, the discovery of radioactivity, he was wrong, but he also won a Nobel Prize for that. And then just a few years later, radium and polonium were isolated by the Curies, who are shown here. Marie Curie, possibly the most famous radiochemist, and her husband Pierre Curie, who also was a Nobel laureate at the time. So Marie obviously went on to win 2 Nobel Prizes, if you remember from your history. Right about the turn of the century, in 1899, Ernest Rutherford identified the alpha particle. The radiation was divided into alpha, beta, and gamma components, and it was based upon the ability of these different radiations to penetrate objects. So alpha penetrated an object the least, beta a little bit more, gamma the most. So alphas could be stopped
by a piece of paper,
beta an aluminum foil, and gamma's very difficult to stop. 1909, the alpha particle was shown by Rutherford to be the helium nucleus. He determined the charge to mass ratio, so this alpha particle gaining more information. 1911, the Rutherford atomic model. Thomson had a plum pudding model that was negated by Rutherford.
Rutherford's team,
they demonstrated some high central charge, small volume, and this was demonstrated by an alpha particle scattering on a gold foil. From this scattering, the hypothesis was developed that, well, the mass must be all concentrated in an area where the particle would impinge upon this nucleus and get scattered back. Detection of alpha particles and detection of other particles was expanded upon in 1912 by the development of the cloud chamber.
And here is an example of a cloud chamber. We see a particle of radioactive material sits in a chamber that contains a supersaturated gas phase, in this case an alcohol. So you can create this by cooling an alcohol with dry ice. As the particles traverse through this supersaturated air with the alcohol, it ionizes the alcohol, leaving tracks which are indicative of the particles passing through it. And this can actually be used to identify alpha and beta particles as they interact with matter differently and will leave different signatures in the clouds. This
And then a planetary atomic model was postulated by Bohr back in 1913. So after the discovery or the postulation of the Bohr model, where the electron orbitals are a little bit better defined than Rutherford's model, 1914, the nuclear charge was determined by X-rays. This was postulated and demonstrated by Moseley, who was working again at Rutherford's lab. 1914, and then you see a gap between 1914 and 1919. The first war stopped a lot of, obviously a lot of research. And in fact, Moseley, who was working in Rutherford's lab, could have avoided the war, but wound up getting killed in France, and really was identified as one of the greatest losses of science due to a military conflict. 1919, artificial transmutation by nuclear reactions was observed. Again, Rutherford. He bombarded nitrogen-14 with an alpha particle to make oxygen-17. Well, nitrogen-14 got from the atmosphere, and the alpha particle was from a radioactive source. He just identified that you could have this nuclear reaction occur. Again, so you can see that Rutherford's lab was putting out a lot of great research, great researchers. 1919, mass spectrometer, first development. 1928, the theory of alpha radioactivity by Gamow, which utilized the concept of tunneling through a barrier to describe the decay. 1930, Enrico Fermi proposed the neutrino hypothesis, where there's a massless particle with a spin of 1/2 that was used to explain beta decay. When we discuss beta decay, you'll see the importance of Fermi within understanding beta decay. 1932, the first cyclotron, which is shown here, which you could hold in your hand, was made by Ernest Lawrence at UC Berkeley. As a graduate of the UC Berkeley radiochemistry program, there's a plaque at the chemistry building on campus at UC Berkeley that describes the radiation lab where these experiments were performed. In 1932, the neutron was discovered by Chadwick, and he used some scattering data to calculate the mass. This led to a proton-neutron nuclear model. Again, this is all at the Cavendish Laboratory. 1934, discovery of artificial radioactivity, the Jolets and the Curies. Again, child of Pierre and Marie Curie, getting involved in the same sort of research. 1938, nuclear fission was discovered. So Lisa Meitner, Otto Hahn, Fritz Strassmann discovered nuclear fission, 1938 in Germany. From people that I'd worked with who were on the Manhattan Project, this was actually a very important consideration, that the Germans had this understanding of fission, that they were fundamentally technically advanced in this area prior to the Second World War. But in 1942, Enrico Fermi and others made the first fission reactor at the University of Chicago. It's called the Chicago Pile. 1945 was the Trinity test, where first plutonium device was tested. And then 1947, radiocarbon dating was explored as a way of dating material. So within this period, the artificial radioactivity was a rather large advancement, show that isotopes that are somewhat different could be formed. And here's an example of a painting from University of Chicago, the first reactor, where it's a air-cooled, graphite-moderated reactor. And then you see the students, the graduate students here, who would be called upon in case the reactor went out of control, where they could help release agents that would control the nuclear reaction. Let's start the discussion on the anthropogenic radionuclides with the two that are below bismuth. Those would be technetium and promethium. Technetium was confirmed through discovery in December of 1936 by work of Pierre and Segre. The material for this discovery actually came from Ernest Lawrence. He had the cyclotron. He had a molybdenum foil in the cyclotron. It was continually bombarded. Molybdenum has 42 protons. The bombardment created material that had 43 protons, which was technetium. And this was known that technetium should exist since there was a hole in the periodic table. And the researchers, Pierre and Segre, at the University of Palermo, successfully separated the technetium from the molybdenum foil, showed that it was different chemical properties, identified the isotopes, and provided the name after the Greek technetium. Eventually, Segre worked with Glenn Seaborg to isolate technetium-99m and used this as a medical isotope. Going to the lanthanides, promethium was first produced and characterized at Oak Ridge National Lab during the Manhattan Project by the researchers listed here. Should be noted that Coriell obtained a Nobel Prize for work that he did with neutrons later in his career. The separation analysis of this material was performed from fission products of uranium fuel in the graphite reactor. The lanthanides are known fission products. So the promethium, as they named it, was produced and identified during the Manhattan Project, although the discovery wasn't announced until 1947. Then other synthetic elements. We'll start with neptunium. If you look at the actinides, you go from actinium, which there are trace natural actinium, thorium, which is naturally available, protactinium, which is part of the decay scheme of uranium, and then uranium, which is also naturally available in mined. So neptunium would be the next element that's synthetic, and it was the first synthetic transuranic element to be discovered, and it was the isotope neptunium-239 was produced by McMillan and Alvison at UC Berkeley in 1940. They bombarded uranium with cyclotron-produced neutrons. So these neutrons were produced by hitting a particle into a beam stop. So for instance, a piece of carbon, any sort of material, extra neutrons would come out. Those neutrons get absorbed by uranium-238. They would make uranium-239. That uranium-239 would beta decay to neptunium-239, which has a half-life of about 2.4 days. They isolated this small amount of neptunium from a large amount of uranium, showed that the chemical property was different than the uranium. However, the chemical properties of uranium, they weren't understood at this time in 1940. The actinide elements were part of the transition series. So uranium was grouped under tungsten. It wasn't until Glenn Seaborg later came up with the actinide hypothesis that moved the actinides where they currently live on the periodic table. But they showed that they showed some similar properties to uranium, but not completely. Eventually, macroscopic amounts of neptunium-237 were produced with a faster neutron on uranium-238. So a neutron would come in, it would knock out two neutrons, it would make this uranium-237. That would beta decay to uranium, from uranium-237 to neptunium-237. And they made 10 micrograms of material. They eventually made much more neptunium. Now one can get, certainly tons of, many multiple grams, kilogram quantities of neptunium-237. Plutonium synthesis was the second transuranic element of the actinides to be discovered. Plutonium-238 was produced in 1940 by Seaborg, McMillan, Kennedy, and Art Wall. Art Wall was the graduate student, so he really did the bulk of the work. And this was produced by using the 60-inch cyclotron at UC Berkeley. So the the diameter of the cyclotron was 60 inches. The reaction was they took a target of uranium-238, hit it with deuterium. 2 neutrons came out. They made this neptunium-238. That neptunium-238 beta decayed to plutonium-238. The oxidation of the produced plutonium showed that it was different than the chemistry of the uranium. They identified the differences in the chemistry of the element. They were able to use the radioactive decay to identify some of the properties, the alpha decay energy, get an idea of the half-life of this isotope. Eventually, in 1941, plutonium-239 was produced, where uranyl nitrate in a wax was behind a beryllium target that was bombarded with deuterium, so a lot of neutrons. The paraffin block would thermalize, would slow down those neutrons. So the uranium-238, in this case, would absorb a neutron, make uranium-239. That would decay to neptunium-239, and that would decay to plutonium-239. There was a separation with fluorides and extraction with diethyl ether, and they showed that, like uranium-235, neptunium-239 would undergo fission with slow neutrons. And for this work, Glenn Seaborg and others were awarded the Nobel Prize. The trans-plutonium element discovery, americium and curium, they were first produced in a reactor by neutron capture. Uranium-238 would be in the reactor, would gain a neutron, make plutonium-239. That would capture a neutron, make plutonium-240. The plutonium-240 would capture a neutron, make plutonium-241, which would undergo beta decay to americium-241. There would also be subsequent neutron capture to curium-242. There are also routes for doing direct production. Plutonium-241 would be produced. It would beta decay to this americium-241, and the plutonium-241 was produced by the reaction of uranium-238 plus an alpha particle. And then you could get another sort of direct production by using the same sort of reaction except with plutonium-237. The way we would write a reaction for the production of curium-242 is shown here, where one took plutonium-239, bombarded it with helium, a neutron would come out, and you would make this curium-242. The chemical separation from plutonium was achieved, and the curium-242 decayed to plutonium-238. They understood the energies and the half-life of plutonium-238. If they saw something decay to it, and they knew that that decayed in alpha, you actually had a genetic relationship. So you could clearly identify a produced isotope from something that had an alpha decay. They did show that they had difficulty separating americium and curium from the lanthanide fission products. They all have the same trivalent oxidation state. And on the web page, there's an announcement on the discovery of these elements. The elements in order to be discovered next are berkelium and californium. One can guess where they were made. A trend that was established earlier, they required targets of americium and curium. So the new elements that were made were then used as targets. They had to get sufficient amount of the new elements. Then they would bombard these targets with an alpha particle. So you would go up to, you use americium to make berkelium. You use the curium to make californium. They separated these from the target material. So again, remember, this is +3 oxidation state. Berkelium actually has a +3, +4 oxidation state, +3, +3 oxidation state. One would do column chromatography. You could calibrate the chromatography system with some lanthanides. But what's shown here is the log of the activity versus the drops of the eluent. And you would see that there's different spikes of the activity. And the lighter the lighter the element, the longer it takes it for it to elute. So the heavier elutes first. And this has to do with the change of the ionic radius. As the lanthanides get heavier, as the actinides get heavier, the ionic radius contracts. So if we use this method to investigate new elements, where would you expect the heavier actinides to elute? Well, anything that's heavier than californium should elute sooner. So that's actually a useful tool, because these heavier elements are going to be made in less amounts, and also tend to have shorter half-lives. So having them come off the column quicker is beneficial for their discoveries. So you can see where you would have these separations. The number of drops coming off a column would be sufficient to collect and identify the different elements. That's where the heavier elements you would expect them to elute. Einsteinium and fermium. Well, we made a little change here. They were actually first produced in the thermonuclear test, the Mike test. You can see information about the Mike test on this YouTube video. There were also new isotopes of plutonium, plutonium-244 and plutonium-246. The thermonuclear test, a hydrogen bomb, you started off with uranium-238 and you made successive captures on the uranium-238. So you go from uranium-238 to uranium-246 in an instant, and then that uranium would beta decay to make different elements along those different isobars. There was an example here of the correlation between the log correlation of the yield versus the atomic mass. So this is an example of nuclear forensics, where one was able to identify information about the yield of a test from the production of different isotopes. This was the first time there was production of trans-californium isotopes. So you would make these heavy uranium isotopes followed by beta decay. They made einsteinium and fermium. And as we will discuss in nuclear processes, this is similar to the R process that stars go through, the rapid process, and how elements are made. And as we described earlier, for americium curium, ion exchange was used to separate these elements. The final three actinides, the heaviest ones, mendelevium, nobelium, and lawrencium, these wind up getting atom at a time discovery, because the amount of target that you can make for these reactions with an alpha particle start becoming less. There's not a lot of einsteinium to start off with. You're not going to make a lot of mendelevium. The cross sections get smaller. So they're requiring a high degree of chemical separation. So what one would do is take the target, bombard it with helium nucleus, put a catcher foil behind the target so that the recoil nucleus would go onto this catcher foil, is usually gold. You would take that gold foil that had the recoiling product on it, dissolve it in acid, then do ion exchange chemistry. There was some controversy with nobelium. It was expected to have trivalent chemistry. It's actually divalent. If you look at how the electrons are filled, by the time you get up to nobelium, so element 102, you have a filled 5f orbital, so 14 5f electrons, and these two 7s electrons are open. So one could remove those two 7s electrons relatively easily. You have a divalent oxidation state, but trying to remove an electron from a filled f orbital is difficult. So nobelium had this divalent oxidation state. The first attempt cannot be reproduced. The final eventual reaction was shown here, where curium-246 was bombarded with carbon-12, 4 neutrons, to make this 254 isotope of nobelium. There was an alpha decay of nobelium. The fermium-250 progeny was identified by its alpha decay, thereby confirming the production of the nobelium-254. I was told by Glenn Seaborg that during this controversy, they knew that the Swedes who were doing the work wanted to name the element after Alfred Nobel. So as a joke, they called it nobelivium. Lawrencium was made from different isotopes of californium bombarded with boron, so stable boron, you get to 10 and 11. And then a new isotope was identified with a 6-second half-life as lawrencium-258. So one could see that there was this trend We've obviously extended that trend to go all the way up to element 118, but the separations become more difficult, the half-lives become shorter, and the probability of the reaction goes down. So we should start by discussing the definition of radiochemistry. There's a few different definitions people use. One could be the chemistry of radioactive isotopes and elements, utilization of nuclear properties in evaluating and understanding chemistry, and one that I like is the intersection of the chart of the nuclides and the periodic table. I prefer this one because it shows that the chart of the nuclides are nuclear properties, periodic table of chemical properties, and as a radiochemist you transition back and forth between nuclear properties and chemical properties. So some of the things that we should understand when we talk about radiochemistry, let's start, since we want to talk about the nucleus and nuclear properties, let's start with that. The nucleus we can always describe as the number of Z protons and N number of neutrons in a nucleus. The diameter of the nucleus is about 10 to the minus 14 meters. And electron interactions with the nucleus, that's going to be the basis of chemical properties. Electrons are, those orbitals are on the order of 10 to the minus 10 meters. So the bulk of the radius and volume of an atom is composed of electrons, but the bulk of the mass, the small area, is occupied in the nucleus. And electrons, they can be excited, they can get into higher energy orbitals, they can undergo ionization. These binding energies of electrons can affect ionization. That changes some of the chemical properties, so different oxidation states. This will come into play more when we talk about the actinides, where there's multiple oxidation states. And that has to do with the fact that electrons are being loaded up into those electron orbitals, and the energy differences between the different orbitals are very small. So some of the terms that we have for atoms within radiochemistry, we've already discussed. Isotopes. So an isotope is the same Z, so the same proton number and different neutron numbers. An isobar, where we have the same A, the sum of the protons and neutrons. So as an isotope undergoes beta decay, it converts a neutron into a proton. So the sum, the A, remains the same. An isotone, that's the same number of neutrons but different number of protons. This is used to help identify how the neutrons and the protons have properties within the nucleus. And then something we've already mentioned, the isomer. So technetium-99m, that little M state, and it's a nucleus in an excited nuclear state. And the one way that we can describe a certain isotope is to have, as shown here, a chemical symbol with A, Z, the proton number, and possibly the neutron number listed here. Another term that we've described is the half-life. And the half-life is the amount of time it takes for half of a radioactive material to disappear. So for instance, if one has some iodine-131 and you measured that it was 25 milligrams, how long would it take it to go from 25 to 12.5 milligrams, to 6.2 milligrams, to 3.1 milligrams? Each one of these is cutting down by a half. It's first order decay. There's actually a fundamental relationship that's shown here, where the number of, in this case, atoms, but if I know the number of atoms, I know the mass at a given time is equal to the amount initial times e to the minus lambda t. Lambda, the decay constant, is just equal to log 2, the natural log of 2, divided by the half-life. Now, if this time is in seconds, your half-life needs to be in seconds. If this time is in minutes, your half-life needs to be in minutes. In this first-order decay, this half-life term is fundamental in radioactive decay. Again, this is an equation that we will see frequently in the. For the boundary of the course, we're really going to go up to the forces in nature. In nature, there are 4 fundamental forces: gravity, electromagnetic, which you likely have seen before. Then weak interaction, and then strong interaction. Weak interaction is used in beta decay, where neutrino interaction produces beta decay. And then strong interactions are nuclear properties, forces that hold the nucleus together. And we're going to explore and discuss nuclear properties and beta decay in terms of these fundamental interactions. So with these fundamental particles in nature, there are interactions, symmetries, and properties of particles that are consistent, that are used within nuclear physics and derived from some of the early work and continue to be utilized today. So particles can be classified as fermions or bosons. So fermions obey the Pauli principle. They're antisymmetric wave functions. They're half-integer spins. Particles that are fermions include neutrons, protons, electrons, all half-integer. Bosons do not obey the Pauli principle. They have symmetric wave functions and integer spins. So for instance, photons. We're going to utilize some of these properties in discussing transitions. As you can imagine, neutrons, protons, electrons, they're all involved in decays, and photons are involved in gamma decay. The standard model is shown here, where you've got a nucleus, as we described, quarks, that 3 quarks make up a nucleon. So a proton, shown here, 2 up and a down quark, a neutron, 2 down and an up quark, an electron much further out. Information on the quarks are shown here. Leptons include electrons and neutrinos, different flavors of electrons and neutrinos, including the electron neutrino, the muon and the muon neutrino, the tau and the tau neutrino. Bosons are force carriers, so photons, W and Z bosons, gluons, they have integer spins. As an example from this, what are the quarks in a proton and a neutron? As shown here, there's 2 up, 1 down quark in a proton. So the up has a charge of 2/3. The down has a charge of -1/3. And if I had something that had 2 ups and a down, I'd have a charge of 1. If it was neutral, well, I would have 2 downs and an up. And imagine that through beta decay, where a neutron gets converted into a proton, at the subatomic level, you have transition. So a neutron, an up and 2 down quarks, converts to a proton. One of these down quarks gets converted into an up quark. Okay, so in both lectures, a review of the topics presented here includes a history of nuclear physics research and radiochemistry, how it grew, and how the properties of the nucleus were evaluated and discovered. We'll go into that in the course and show how the nuclear data was used to understand the properties of the nucleus. We talked about discovery methods of radioelements, the methods and techniques. One of the techniques was you use some of the elements you produced earlier to make new elements. Types of radioactive decay, alpha, beta, gamma, spontaneous fission, electron capture. We also discussed the difference between gamma rays and X-rays. We gave some examples of how to utilize the data presented in the chart of the nuclides and table of the isotope. We talked and demonstrated some of the fundamental decay equations. If I know the half-life of something, I know the initial amount. At a given time, I can predict how much is remaining. And we identified some common fission products. We did that through understanding the double-humped fission curve, plus looking at the chart of the nuclides, understanding which isotopes would be produced in fission. Okay, some examples of questions that you should be able to answer include what's the outcomes of the courses, and the course outcomes are listed here. Include fundamentals of nuclear structure, chemistry of the radioelements, modern topics in radiochemistry. Discuss the discovery of radioactivity, Becquerel and the Curies, used this uranium salt, exposed it to sunlight. And how about the first man-made reactor, 1942, the Chicago pile. I'm from Chicago, from the South Side, University of Chicago, same area. It was a graphite moderate natural uranium reactor. We'll describe how the moderators, either water, deuterium, or graphite, influence the behavior of neutrons in a reactor.
Other questions you should be able to answer include, what are the radioelements? As is shown here on the periodic table, all elements with a Z greater than 83 are radioactive, hence they're only available as radioactive isotopes. And there are two elements with Z less than 83, technetium and promethium, which are also only radioelements. You should also be familiar with the different types of radioactive decay. These include alpha decay, beta minus decay, gamma decay, positron emission, electron capture, and spontaneous fission. At this point, you should really know what these types of decays are in a very general sense. Subsequent lectures will describe these decay routes in much more detail. And finally, you should have an idea of what are suitable references for information on the isotopes. Good references that we've discussed in this lecture include the chart of the nuclides, which shows information on each isotope, and the table of the isotopes, which provides detailed information including nuclear structure and information related to radioactive decay.
I hope you enjoyed the first lecture. When you have completed it, please comment on the blog and respond to the Lecture 1 quiz. The information was primarily introductory for this lecture. We discussed data sources, including chart of the nuclides, table of the isotopes, and the isotope browser. As we explore more topics in the course, we will use the information in these data tables in equations related to radiochemistry. The information you should be able to comprehend from this lecture includes the meaning of half-life, types of decay modes, differences between gamma rays and X-rays, and you should be able to identify some very fundamental data from the chart of the nuclide and other available sources. This includes decay modes and resulting progeny, and the isotope half-life or their stable abundances.